How you doing, guys, and welcome to today's tutorial. Today's tutorial will be on the skeletal system and the 206 bones and cartilage that make up the human skeleton. We're also going to take a look at the different functions and the names of the different bones of the skeleton, and we're also going to look at anatomical terms, locations, and also the little anatomical actions. We're going to take a little look at the different bone structure, the different shapes of bones, and also the different types of joints we have. So let's look at the functions, and we have many functions of the skeletal system, but we can condense these down into 5 main functions. The first being support. So this gives us shape, it gives us structure, it holds us up. We also have movement because your skeleton acts as a scaffolding or as a framework for muscles, and these muscles will attach onto the bones and cause movement when they contract, so it works with the muscular system. We also have muscle tissue in the body that's responsible for moving things like blood, fluid and waste. Function number 3 is protection, and we have different bones in the body that protect vital organs like our brain, our lungs, our heart, and we also have the spinal cord, obviously, that needs protecting. So we have bones that wrap around these to protect. Our blood cells are produced in the bone marrow of these bones, so blood cell production would be a function of the skeletal system. And we also eat, digest, and then store calcium or minerals in our bones. So storage of calcium would also be a function of the skeletal system. Now, before we name the individual bones, it's important to know that we have 2 parts of a skeleton. So we have everything down the center called the axial skeleton. And this will include things like the skull, our ribs, our spine, our breastbone. And then we have the appendicular skeleton, and this is our appendages, so our limbs and the girdles that hold the limbs in place. So if you want to follow along with this, we can follow along on our PDF of the student workbook. And we can turn to page 5 on the skeletal system. If we look on page 5, we can see that we have the axial skeleton on the left and the appendicular on the right. So let's take a little look at the axial skeleton first, and we can see here we have the skull, we have the vertebral column that runs down, we have these ribs that run off the vertebral column, and then we have our breastbone in the middle. So it's also important to see that on page 7 of our student workbook, we have a picture of the skeleton, and these are labelled 1 to 20, but we actually have 21 bones here with 2 12s. So take a look at the 12 on the skeleton's left hand, which is hanging by its side. 12 is pointing to the wrist, so this is going to be 12A, pointing to the wrist. And then in the skeleton's right hand that's waving at us, we have another 12 pointing to the bones in the hand. So this is going to be 12B. 12B is pointing to the bones in the hand. Let's look at 1 then first, and we'll name it in layman's terms first. So 1 will be the skull, and then we'll give it its correct name of the cranium. 2 is pointing to the jawbone, and its correct name would be mandible. And then we have 3 pointing to the spine, and these are made up of individual bones called vertebrae. And when they're all put together into a column, we'll call it the vertebral column. 4 is pointing to our ribs or rib cage, and that does stay the same. Ribs is fine. And then we have 5 being the breastbone, the place where all the ribs meet up in the middle. That protects our heart. We call the sternum. So that's the 5 bones in the axial skeleton, everything down the center. We have the cranium, the mandible. Then we have this vertebral column that extends down from the cranium. And then we have these ribs that sit on the vertebral column, and then they all meet at the sternum. Now let's take a little look at the appendicular skeleton, and these are the girdles of the upper limbs and the upper limb itself. And then we have the girdle of the lower limbs and then the lower limb itself. So the arms and the legs, and then the bones that hold them into place. So 6 on our skeleton on page 7 is pointing to the collarbone, and the correct name for the collarbone is clavicle. Then we have 7 pointing to our shoulder blade, and the shoulder blade is called scapula. 8 is pointing to the long bone in the arm, and that's called the humerus. And at this point, it's important to know that we do have an anatomical position. So the anatomical position, and when the skeleton is standing upright with the feet together, the arms are by the side, palms are forward, thumbs facing out to the side away from the body, and the fingers extended. And from there, we can see that we have 2 bones in our forearm. We have one on the outside and then one on the inside. So 9 is pointing to the forearm bone on the inside, and this is called the ulna. And then 10 is pointing to our hips. This, for the time being, can be called pelvis or pelvic girdle. And then 11 is pointing to that other bone in the forearm on the outside that goes to the thumb. So the outer bone, or the most lateral bone in the forearm that goes to the thumb, is called radius. Now we're at the 12, so we have 12A first, and 12A is pointing to the bones in the wrist. This is made up of 8 short bones we call carpals. And then an extension of those are the 5 bones in our hand. So 12B are pointing to the 5 bones in each hand. So we have 10 of these, and these are called metacarpals. At the end of our metacarpals, we have these digits that we call fingers, and as a group of bones, these are called phalanges. Now we're into our lower appendicular skeleton. We've already mentioned the pelvis. So the long bone that's connected to the pelvis is bone number 14, we call the thigh bone. This is the longest bone in the body, and any long bone in our body has a shaft that has a hollow center, and then 2 knobbly bits at the end. So the shaft is called diaphysis, and the 2 bits at the end are called epiphysis. And each long bone has them. So bones can be short, like our phalanges, and they are technically long bones because they have a little shaft, and then we have these epiphysis at the end, and that's what we can feel when we're feeling our knuckles, the lumpy bits. But the thigh bone, being the femur, is our longest bone in the body. And then at the end of the thigh bone, we have this little sesamoid bone, and sesamoid means it floats. And we have this floaty bone called the kneecap. And the correct name for the kneecap is patella. Below the knee, then, we have 2 bones in the lower leg, just like the bones in the forearm. We have one medial and one lateral, and we have the same in our lower leg. So 16 is pointing to the main shin bone, the larger of the 2 bones in the lower leg, and that is called the tibia. And then the smaller bone that sits lateral to the tibia on the outside is called fibula. And at the bottom of these 2 bones, the tibia and fibula, we have more short bones, 7 short bones this time, and these are called tarsals. So we don't confuse these with our carpals in the wrist. So if we think toes, T for toes, T for tarsals. The tarsals are closer to our toes. And then we have an extension of these, so we have 5 in each foot, bones of the foot, and these are called metatarsals. And then at the end of our metatarsals, we have these digits like we have in our hands, we call toes, and when we were naming these, somebody got really bored or run out of ideas and decided to call them phalanges too. Okay, so if we put all these bones together and look at the skeleton has a rather unique shape, and that's because all the bones that make up the skeleton are all different shapes and sizes. So let's look at the shapes of bones. Now we can turn to page 8 in our manual. Let's come up with some shapes and some examples. So I've mentioned the long bone before. the femur being the longest, and a long bone is anything that has a shaft and then these two knobbly bits on either end. We have short bones, and these are like short little cuboid bones, really dense bone tissue. And then we have flat bones. Most flat bones in the body would be protective bones, but we do have other irregular looking protective bones also. And then we have things that don't fit into any other shape category, they just look kind of irregular, and they're irregular bones. And then we mentioned the kneecap earlier on being a sesamoid bone. So a sesamoid bone is anything that's not wired direct to another bone, so they kind of float, and they're encased in ligament and tendons, and they kind of float in bones. So an example of our long bones would be femur and fibula. But like I said before, our phalanges are made up of rather short, long bones. So anything that has a shaft and then knobbly bits would be long bones. And then we have short bones. These are cuboid bones. We find these in our carpals and tarsals. We have flat protective bones, so things like our scapula, our pelvis, and our ribs. Ribs look like long bones, but they haven't got a hollow shaft and they don't have epiphysis at either end. So there's no lumpy bits, so they are flat bones. And then we have bones in our cranium bones. Certain bones in the cranium would be flat bones also. Irregular bones then would be things like our vertebrae, our mandible, so anything that looks kind of irregular looking would be irregular. And then, like I said, we have our kneecap or our patella being the sesamoid. We also have another sesamoid bone called hyoid, and this is a little floating bone that sits in a throat at the base of a tongue, and this isn't wired directly to another bone, so it does float. It allows movement for a tongue so we can talk and swallow food and such like. So here's a little look. We can see A is pointing to a long bone, and the example of that one there is our humerus. Then we have B pointing to short bones, so these little cuboid bones in our wrist we call carpals. And then the example of a flat bone would be the parietal, so the bone that's at the top side of our head or our cranium. And then we have an irregular, so we can just see one vertebra there, so we can see the body and those spinous processes look quite irregular. Okay, so these bones are all held together. When two bones meet, it's a joint. So a joint or an articulation is a place where two or more bones meet. And how they meet and how they're wired together will depend on what joint they are. So we have three categories of joints. We have ones that don't move at all. These are fixed, so they're fused together. They might have been individual bones at birth, but they fuse together over time. Then we have ones that move just a little bit, so these are semi-movable. They don't really move the skeleton, but there is movement there. And then we have freely movable joints, and these are the ones that move free and are responsible for moving our skeleton. Okay, so fixed joints first. No movement, like I said. They fuse together, and these are only present to facilitate childbirth. So an example of these would be our cranium. So these would fuse together, so it allows for easy passage. Also, it's going to allow for growth of the brain. And then our pelvis is made up of numerous bones, and also they fuse with the bottom of the spine. So it's just there to facilitate childbirth. We have semi-movable joints, so we can see these by a pad of cartilage. So this pad of cartilage stops the few bones from fusing together, so they remain semi-movable and not fixed. And an example of this would be between the vertebrae. We have these pads of cartilage between individual vertebrae. So there is slight movement in our vertebral column, but because each bone moves a small bit over the whole length of the vertebral column, we can get a good bit of movement. And then between pubic bones, so we have this pad of cartilage between the left and the right hip bone, where they meet in the middle. Also, if we looked at our ribs on page 7, these rib bones all meet with cartilage, and the cartilage will go into the sternum. So this allows for expansion of the rib cage also. And then we have freely movable joints, which we're interested in. And 5 is a magic number for the skeletal system. So we have 5 functions, we have 5 shapes, and now we have 5 freely movable joints. These are also called synovial joints because of the synovial membrane that encapsulates them. And there's a large amount of movement in these ones. These are the ones that are responsible for movement of the skeleton. And inside this capsule or joint cavity, we have this synovial fluid that secretes it. So we have a synovial membrane that wraps around these, and that synovial fluid is important because it gives us lubrication and absorbs shock. So we'll take a few notes on synovial fluid. So it's clever stuff. It can become less viscous when you need it to become less viscous. So if we jump and we absorb shock, it can stiffen up instantaneously, and then we can get it to become less viscous by becoming a little bit more watery or less thick as and when we need to. So when we lubricate our joints or do joint mobility, it will become less viscous. It's really important for lubrication, and it will provide nourishment to the cartilage because the cartilage doesn't have its own blood supply. So it does need a good synovial membrane, and then when this breaks down, it's going to cause problems with our joints, like things like arthritis and stuff like that. It's also responsible for cleaning and removing debris and waste bone and stuff. So the 5 major types of synovial joints or freely movable joints. And if we turn to page 9 in our work manuals, we can see the pictures of them there. And 1 on our manual on page 9 is pointing to a ball and socket. 2 is a hinge joint. 3 are gliding joints. And 4 is an example of pivot joints. And then we have 5 is a saddle joint. So before we come up with examples, let's just look at them a little bit closer. So here's a picture of a ball and socket. We can see the ball going into the socket there, and the example here is the femur, so we have the femoral head going into the pelvis. And a ball and socket joint allows for radial movement in almost any direction, and we find these in the hips and shoulders. So our shoulders have a little bit more mobility, but they're less stable. We have more stability in our hip joint. Then we have the hinge, and we can see there a hinge on a door. It will either open or close, and that's very similar to our elbow. So we've got a picture here of our humerus. Then we can see the ulna coming into contact with the humerus, and this is either going to flex or extend. So a hinge joint allows for extension and flexion of an appendage, and this is going to be movement in a single plane. And examples of this are elbows and knees. This one particular one here in the picture is an elbow. Then we have these gliding joints, and if we can see here, this is in sort of cuboid short blocky bones, sort of mid-tarsal or mid-carpal, and we can see here this is in the bones of our ankle. And these slide past each other in different directions, but they don't really open and close. These are more slidey or gliding joints. Now we have a pivot joint, and we can see on the left we have the one in our forearm. So the pivot joint between the radius and the ulna. So the ulna will stay still, and the radius will twist against the ulna, and that will allow us to turn our palms over or upwards. So we can go pronate or supinate our forearm, and this allows us to use things like a screwdriver and stuff, that twisting, taking the lid off a jam jar. And then we have another one on the right, we have in our head. So our top two vertebrae and the spinal column, one sits into the head, and that will spin or twist around the second bone of the vertebral column, so the C1 and C2. And this allows one bone to twist or rotate against another stationary bone. So like I say, in the forearm between the radius and the ulna, the radio-ulnar joint, that will turn our palms down or up. We can do that, or we can look left and right in our head. Then we have the saddle joint. So if we look closely here, it looks like we have a saddle sitting up, and then we have another saddle turned over. So these are both concave and convex, and they sort of complement each other. So this gives us a nice little twisty, slidey, swivelly motion, and we can see here in our metacarpal of our thumb, and that's why we have wider range with our thumb than we do the rest of our fingers. Okay, so those examples then of our synovial joints, and two examples would be shoulders and hips of a ball and socket, elbows and knees of a hinge, wrist and ankles or hands and feet for the gliding, the atlas and axis, that's C1, C2 in the vertebral column, the top two cervical vertebrae, and then our radio-ulnar joint in our forearm, and then we have the thumb or metacarpal of the thumb in our saddle joint. Okay, so anatomical locations and terminology. We mentioned before, so we can highlight this on our PDF of our workbooks. So we have the anatomical position being body upright, feet together, arms hanging by the sides, palms facing forward with the thumbs facing away from the body and our fingers extended. If we remember that, we know what bone is what in the forearm and stuff, and we also know where to find stuff and locate stuff on the human body. So we're going to come across things like anterior. Anterior means towards the front. So if I look at an anterior view of the human body or the human skeleton, it's looking at the front. The opposite then is posterior, and that is away from the front or towards the back. So the posterior view of a diagram would be the back of the diagram. But something can be posterior on the front. So for example, my eyes are posterior to my nose, and that just means basically my eyes are further back than my nose. We have proximal, and proximal means closer to. So if something's in close proximity, it would be close. And what we're referring to is the axial skeleton. The opposite of proximal then would be distal, and that would be further away. So if I were to take my bone in my arm, my humerus, I'd have two joints, a shoulder joint, and I'd have an elbow joint at the other end. The proximal joint is going to be the shoulder because it's closer to the axial, and the elbow joint would be the distal. Now if I were to take my forearm, the elbow now becomes a proximal because it's closer to, and my distal would be the wrist. We have superior, and superior means towards the head or further up. The opposite of that would be inferior. So if somebody's inferior to somebody, they'd be below them, and that's further away. Then we have medial, and medial would be towards the midline. So if we were to take our skeleton and draw an imaginary midline right between the eyes, through the nose, through the mouth, down through the throat, past the sternum, through the navel, and in between the legs down to the pubis, that would be an imaginary midline. So anything towards that midline would be referred to as being medial, and then anything away from the midline would be lateral. So lateral is away from the midline or out to the side. Medial would be in towards the middle. And then we have superficial. Superficial means on or close or nearer to the surface. And the opposite of that would be deep. So that's away from the surface. That's deep inside or within. So any deep muscles we will not see in a diagram because they'd be covered by more superficial muscles or muscles on the surface. Okay, so now we have joint movement and anatomical actions. And these are slightly different to our terminology and locations, okay? So these are how our joints in our body move. And this is important because it's got to be how we move a skeleton. B, it's how we're going to exercise and the movements involved in different exercises. I'm going to list these now, but don't worry too much because next week there will be another video on this, and this would be me demonstrating the actions. For now, let's just take notes and try our best to understand them. Okay, so we have flexion and extension. So flexion would be when I decrease the angle of a joint. So if I was to have my arms by my side, and then I've got a long joint or a big angle in my elbow joint. If I was to decrease that angle and bend at the elbow, I would be decreasing the joint, and that's bending my arm at the elbow. That would be elbow flexion. If I was to do the opposite and increase that joint, then I would be straightening my arm, and that would be elbow extension. I can also do that at the knee, so I can decrease the angle at the knee and bend at the knee, and that would be knee flexion. And the opposite of that would be straightening the leg, knee extension. I can do this also with my shoulder. I can bring my arms forward, and that will bend the shoulder, and flex my shoulder forwards, so forward flexion, and that would be shoulder flexion. If I was to bring my arm backwards, back to the center and beyond, further back, and push my arm away from the body backwards, that would be shoulder extension. So a frontal raise, if I was to raise my arm to the front, that would be shoulder flexion. If I was to bring my arm back and push it backwards, that would be shoulder extension. I can also do this with the hip, so I can raise my knee up, like I'm going to lift my knee up to the waist height or do high knees, and that would be flexion of the hip, so hip flexion. If I was to bring my leg down, back to the ground or through, that would be hip extension. So if I was to kick a ball forward, it would be hip flexion. If I was to backheel a ball backwards, it would be hip extension. I can also flex my spine. So if I was to go forward and to go down and bend my spine and touch my toes, that would be spinal flexion. If I was to extend back and look up and behind me, that would be spinal extension. So that's flexion, flex forward or extend back. But we can also flex sideways. So if I was to bend at my spine and reach down and touch the outside of my knee with one hand, that would be lateral flexion. So lateral being out to the side. I can also touch my ear to my shoulder. That would be lateral flexion. There's no lateral extension, it's just flexion. I either flex left or flex right laterally. The next one is abduction, so abduction, and adduction, AD. So abduct would be to take away. If I was to abduct something, I would be taking it away. So if I was to bring my arm outside, laterally, away from the body, it would be going away from the midline. So to take away from the midline would be shoulder abduction. I move my arm out to the side, and the movement happens at the shoulder abduction. If I was to bring it back and add it towards the midline and through the midline, it would be shoulder adduction. I can do these with my hips as well. So if I was to stand on one leg and kick my leg out laterally to the side, away from the midline, it would be hip abduction, so abduction. And then if I was to bring it back and add it towards the midline or through, it would be hip adduction. I can also do these with the scapula as well. So if I was to pull my scapula together in towards the midline, it would be scapular adduction. And then if I was to pull them apart, so round my shoulders forward and pull my scapula away from one another, that would be to abduct it away from the midline. So it would be scapular abduction. We always put the joint and then the movement. So elbow flexion, scapular adduction, for example. Okay, now we have horizontal flexion and horizontal extension, and this is the same as regular flexion and extension, only we're standing in a horizontal plane. So we're only really going to worry about this for the shoulders, for example. So if I'm going to stand up, put my arms out to the side horizontally and form a T. Now if I was to narrow the angle of my shoulder and bend my shoulder forward, that would be horizontal flexion. If I was to stand with my arms in front of me and pull them back to the T and beyond, it would be horizontal shoulder extension. So this is like regular flexion extension, just when I'm moving it horizontally. Now we have two types of rotation, so take a note of these. First rotation is very straightforward. If I was to look left over my left shoulder or look right over my right shoulder, I would just be rotating my head left and right. That's side to side rotation. I can also do this with my vertebral column. So if I was to stand with my feet stuck to the ground, I could rotate my torso to the left, or I could rotate it to the right, and that would be spinal or trunk rotation, side to side rotation. So that's the first type of rotation. The second type of rotation will happen at ball and socket joints. So if I was to stand with my arms, flex at the elbow, so I have my hand in front of me. Now if I was to turn my hand in towards the midline or away from the midline, I'm rotating my shoulder joint. So try this, put one hand on your shoulder joint and bend the other hand at the elbow and then just twist in and out. We can feel the head of the humerus rotating in and rotating out. Move your hand in towards the midline. That would be medial because it's going towards the midline, so medial shoulder rotation. Bring your hand out away from the midline. We're going to move it lateral, and that would be lateral shoulder rotation. And we can also do this at the hip joint as well. So if I was to stand with my leg straight and just turn the whole leg and rotate it inwards, turn the foot in towards the midline, it would be medial rotation. If I was to turn it away from the midline and rotate it outwards and open up my hips, it would be hip lateral rotation. So they're the two types of rotation, folks. We have side to side, which is straightforward rotation, or we have medial and lateral rotation. Rotation of the ball and socket joint in towards the midline would be medial rotation, and then away from the midline would be lateral rotation. It's either going to be shoulders or hips. Next we have plantar flexion, dorsiflexion. This is fairly straightforward, folks, because this is only going to happen at the ankle. So if I was to point my toe away from my shin, that would be plantar flexion. The opposite of that is dorsiflexion. So if I was to pull my toes back towards the shin, it's going to be dorsiflexion. So if I'm standing up and I point my toes, obviously the floor can't go anywhere, so that's going to elevate my heels into a calf raise, and that's plantar flexion. I've pointed my toe. If I was to pull my toes back towards my shin and stand on my heels, that would be dorsiflexion. So plantar flexion, dorsiflexion only happens in the ankle. These two, ankle inversion and ankle eversion, these only happen at the ankle also. So if I was to invert or cause ankle inversion, I would be turning the sole of my foot in towards the midline. So twist, so the outside of my foot goes lower and the inside of my sole turns in towards the medial line or that imaginary midline. The opposite of that then is ankle eversion, and if I was to evert my foot, I'd be turning my ankle so the sole of my foot is away from the midline out to the side laterally. Now we have pronation and supination, and these only happen in our forearm. So if I was to pronate or cause forearm pronation, I would turn my hand so the palm was down. And supination is turning so my palm is up. So a prone position would be if I was lying face down. So an example of this would be a plank. And then a supine position would be lying face up. So I'd be on my back doing a crunch. But when we talk about pronation and supination, it refers only to the forearm. Pronation being palms down or an overhand grip, and supination be palms up or an underhand grip. And then the last two we don't have on our PDF manual on page 11. We're going to make notes of this ourselves. We have elevation and depression. And if we were to be elevated, would be up. If we were to be depressed, would be down. Okay, so elevation would be lifting, and this is only referring to the scapula. We lift the scapula up. Scapular elevation, so if we were to shrug our shoulders, it's because the muscles pull the scapula up, and that scapula is connected to the rest of the bones in the shoulder, so we shrug our shoulders. But it's scapular elevation. If we were to pull our scapula down, it would be scapular depression. So your scaps will move up and down, and also they can abduct and adduct, like we said before. They can go in towards the midline, scapular adduction, or away from the midline. We can pull them apart, scapular abduction. And if we look on pages 12 and 13 of a manual, we do also have a few different pictures there. So it'll show you some examples of what plantar flexion is, or dorsiflexion, or hip abduction and adduction and such like. So there's some examples there. But like I said, I will do another video next week where we'll go over these again and show you one more time. This is something that people don't get straight away anyway, so don't panic if it takes a few weeks for this to sink in. Okay, let's move on to structure of bone then. So this is on page 14 of our manual. So here we can see 1 is pointing to this hollow shaft. 2 is pointing to the outside sheath of the bones. And 3 is pointing to this dense tissue. And then 4 is pointing to this honeycomb section. These all have different names. So let's have a little look at what 1 is pointing to. 1 is pointing to the medullary cavity. And this is that hollow center point in the shaft of long bones. So in the diaphysis of long bones, we have this hollow center, and that's the medullary cavity. 2 here is pointing to the tough outer sheath, and the tough outer sheath is white in color, and it's called periosteum. And this gives bone its white color. Bone would be kind of yellow, but this gives it its white, and it adds a little bit of extra toughness, and it also adds a little attachment site for muscles. 3 is pointing to the dense tissue. Now bones have 2 types of tissue. We have real dense stuff that's really hard and it looks real closely knit, called compact bone. And we have this stuff on the outside. We find these on the outside of long bones, but we find this tissue in all the other bones. Flat bones, sesamoid bones, irregular bones will all be made up of this, and it's called cancellous tissue. Now all the other bones, flat bones, irregular bones and sesamoid bones, would be made up of cancellous tissue. Then there'd be a thin little outer layer of compact bone for added strength. Short bones will be all compact bone, and then in the long bone, which is a good example because it has all the tissues, it has a medullary cavity in the shaft of the diaphysis, compact bone in the shaft, periosteum being the white skin, and then cancellous bone tissue being that spongy bone at the end of long bones. This also contains bone marrow, so let's make a few little notes on them individually. So we have the medullary cavity, which is that hollow center in the shaft, and this contains yellow bone marrow. So in infancy it would start out life like red bone marrow. The only difference is as we get older it gets a little bit more fatty. Then we have the periosteum being the skin or the tough sheath that covers bones. Three was pointing to the compact bone, And this contains blood vessels, so the blood will from the shaft will from the cavity will penetrate this and get it into the circulatory system, and we're going to find it in the shaft of long bones, but also the outermost edge or layer of all the other different types of bone. Cancellous then appears sponge-like, and this will contain our red bone marrow, and we find these in all bones and at the ends of long bones, probably with the exception of our short bones. But the important thing to take away from this, folks, is where would we find compact bone tissue? In the shaft of long bones. Cancellous tissue contains bone marrow and its spongy appearance, and we find it in the end of long bones. Okay, so all these bones are held together with connective tissue, and the connective tissue in the skeletal system are ligaments. So ligaments are like tendons, but we don't confuse the two. So tendons is the connective tissue in the muscular system, ligaments are the connective tissue in the skeletal system. So what are ligaments? It's connective tissue that is responsible for connecting bones to bones. So if we look at this, this is the person's left knee, and we know it's a left knee because we have the femur here, we have the tibia here, and that little bone on the outside, the lateral bone, is the fibula. So look at all this connective tissue that holds the fibula to the tibia, and then on this lateral collateral ligament that connects the fibula to the femur, and then we have on the inside of the knee we have this medial collateral ligament, and this connects our tibia to our femur. We also have these that a lot of people would have heard of, our cruciate ligaments. So we have the one here and then the one here. So the one furthest forward is the anterior cruciate because it's forward, and then the one that's further back is the posterior because it's further back. So what are ligaments? Connective tissues that join our bones to bones. Okay, calcium is another, or storage of calcium is another function of the skeletal system, and this calcium has many functions in the body. So we eat it, we lay it down, we store it, and then we use it as and when it's needed. And for all chemical reactions in the body, calcium needs to be present. So apart from strengthening bones and teeth, which is the obvious one, our muscles wouldn't contract, our nerves wouldn't send the right signals without calcium being present. It regulates our blood acid balance, and it's really, really important for kidney and brain function. So many cell processes rely on the presence of calcium in the body. We don't need to write this down, guys, but if we look at the bottom of page 14, we can just highlight it if we like. We have calcium that's laid down in the bones because we eat it. It gets into through our digestive system, into a circulatory system, and brought to the bones where they're stored. It's released into the bloodstream as required, and this is a constant process. So as we eat it, we lay it down, we use it for all different functions. If there's an imbalance, if there's more going out than coming in, that's going to cause something, and that's going to cause our bones to be brittle. So if we use more, or there's more going out than coming in, that may lead to things like osteoporosis. Osteo referring to the bone, porosis being porous. So that just means porous bones or holy bones. Or we call it brittle bone disease. Now, obviously, it's not as simple as, oh, let's eat more calcium. If we have a deficiency in calcium, which is what osteoporosis is or caused by, then it'd be like the builder going to a sink with a hole in his bucket. He can stand under that tap all day long filling it, and that water is going to leak. So if there's a deficiency, it's not just a case of, oh, I need to eat more cheese or drink more milk. Okay, so now we're on to the pelvic girdle, guys. And like I said before, we're going to name these bones. This is your pelvic bones or pelvic girdle. Here we have the spine at the bottom, and we'll take a closer look at the spine in a little while, and then it goes into these fused bones. So this is the bottom of our spine. Then our pelvis is made up of this left bone and the right bone. Or as we look on our right, it's actually the person's left hip bone. But it's made up of three bones. We have this hip bone here, superior bone in the hip, and that's called the ilium. And then it connects down to this. These are fused together after infancy, and this is called your pubis or your pubic bones, and this is the pubic symphysis where your left and right meet. Then at the bottom we have this seat bone called the ischium. So ilium, pubis, and ischium. Let's take a note of them then. So they're formed by two innominate bones because these bones don't really have a name. They're just the left hip and right hip bone. But these each consist of an ilium, being the hip, the ischium, being the seat, and then the pubis, being the pubic bone. So there are 1, 2, 3 on your diagram on page 15. And if we were to keep it simple, we can just say top, bottom, and middle. So ilium is the most superior bone in the pelvic girdle, ischium being the most inferior, and then pubis being that bit in the middle where the two innominate bones meet. So that's the pelvic girdle, and that brings us on to our last section, the vertebral column. Now, vertebrae is plural, vertebra being single, and let's have a look at one single vertebra. We have this section here, this is the body, so these are the building blocks or the little stacking blocks of our vertebral column. We have a hole in the center here, and this is a lovely little hole that's going to sit our spinal cord, will travel down through this, which is going to give us little gaps at the sides in order for our little nerves or our peripheral nerves to run out the side. We have these spinous processes here, so our transverse processes running out the side, and then we have these spinous processes at the back, the pedicles at the back of our spine, and these will look different depending on what region of the spine they're in. The neck ones or the ones in the cervical vertebra won't look the same, they'll be less spiny, and they'll certainly be a lot smaller because the further down the spine, the bigger they'll be, the stronger they need to be. Okay, so we can see that there's two here together, two bodies, and then we have this paracartilage in between the two, so this is a semi-movable joint, and that's the intervertebral disc. So these stop the two bones coming together, and that's one way the body will absorb shock. And then we can see the spine running down with this peripheral nerve sticking out the side, and then we have our spinous processes and pedicles. If we were to look at the vertebral column as a whole, we can see that it's S-shaped, and that's the other way that the vertebral column will absorb shock. So the first one was the intervertebral discs to stop the bones from coming together, and they will absorb shock. And then the fact that it's actually its own actual or natural S shape will act like a shock absorber. It acts spring-like. If it was perfectly straight, there'd be an awful lot of pressure with gravity on it, but the fact that it's spring-like acts as a shock absorber. And this is made up of 33 bones. We have 7 cervical bones or cervical bones, and these are the bones in the neck. So you see 1C2 was your atlas and axis. We said they pivot, or one pivots around the other, enables us to look left and right. And then the rest of them will either flex or extend or laterally flex to the side. So that's the 7 cervical vertebrae. Next we have 12 bones in the thoracic region. We have 12 pairs of ribs, so we have 12 thoracic bones, and that's what they do. They support the rib cage. We can see that they're getting bigger as they go down. So our cervical are the smallest ones. They're only supporting the head. Now these are holding on a rib cage and an awful lot of weight inside the rib cage because we have vital organs and stuff like that. And then we have our lumbar bones. Our lumbar bones are these 5 bones at the bottom. These are the biggest of all the bones in the vertebral column, and they need to be. There's less protection here, and they're holding up an awful lot of weight above them. So that's 24 true vertebrae. That's vertebrae that have a pad of cartilage between and they independently move. So 24 true vertebrae. Then we have sacral bones at the bottom. So that section there is your sacrum, and that's made up of 5 fused bones. And these are the bones that articulate with the 2 innominate bones of the pelvis to form the pelvic girdle or the pelvic ring. And then we have our coccyx bones, our kind of useless bones now. We don't use them anymore. It's a tailbone, and we have 4 of them at the point of our spine. So the fuse bones at the bottom, 5 and 4, that's 9 fuse bones, along with the 24 true vertebrae, make 33 bones in a vertebral column. Let's take a look at the functions then of the vertebral column, and we can put just a few functions as a whole, but we will divide them up into sections. So your cervical, what are they responsible? Well, they're responsible for support and movement of the head or neck. Your thoracic are responsible for the support of the rib cage, and then we have our lumbar region. So we have movement here, a little bit of movement, and we also have some unwanted movement. So when we talk about posture in future tutorials, we'll look at the way we have unwanted movement of the pelvis. It can either twist down or it can rotate backwards. So we can have a pelvic tilt, and this is going to lead to all sorts of different postural deformities. So our pelvis is supposed to move, but sometimes we do get unwanted movement, or not our pelvis so much as our spine. And then we have the sacrum. So this is responsible for transmitting the weight of our body through the hips and into the legs. So if this doesn't function properly, we can get too much weight going through one side of the hips, and we can get a bit of an imbalance going on there. And as a whole, the vertebral column is going to protect our spinal cord first and foremost, and then it's going to act like its own natural shock absorber because it's natural S shape, as well as the articulating cartilage between the bones. So that's the vertebral column in completion. That's part 1 of the skeletal system in completion. Good luck, guys.